The sky opens like a dark plain with stars scattered edge to edge. What if some of that darkness hides doorways, shortcuts through space-time itself? Wormholes aren't fantasy notes. They arise from Einstein's general relativity. The first kind, the Einstein-Rosen bridge, looks inviting, but collapses the instant you try to cross. Could a passage stay open? Kip Thorne's proposal points to exotic matter with negative energy never seen, yet not ruled out by quantum mechanics. If it exists, distance could fold, and the long road between stars or even moments in time might shrink to a single step. Curious? Tap like and subscribe so others can wander with us. Tonight, we'll follow the math, test the limits, and ask whether the universe quietly keeps keys to everywhere, tucked between relativity and the quantum world. Picture a doorway that does not open into the next room, but into a far corner of the universe. One step, and the long miles between stars fall away. Light would need millions of years to cross that gulf. You would not. That is the idea behind wormholes, tunnels through space-time, the joined fabric of space and time. A wormhole would not be regular empty space. It would be a shortcut, a path that links two distant places or even two different moments. The idea does not come from fantasy. It comes from the same math that gave us black holes, the bending of starlight by gravity, and ripples in space-time called gravitational waves. Those predictions seemed bold when first written down, yet they turned out to be true. So we ask careful questions. Could wormholes exist somewhere in the universe? If they exist, could anything travel through them? To get useful answers, we have to look at how gravity really works, how black holes push space-time to its limits, and where the math allows bridges to appear. Start with the nature of space itself. To our daily senses, space feels empty, like a quiet backdrop where things float. Einstein's general relativity says otherwise. Space and time form a single fabric space-time that can bend and stretch. Mass and energy are what bend it. A planet, a star, even a beam of light carries energy, and energy tells space-time how to curve. Objects then move along that curve. This is a shift from the older picture. Isaac Newton described gravity as a force that pulls across a distance, and his math works well in many cases. But Newton did not say how that pull travels through a void. Einstein replaced the pull with shape. There is no invisible rope. There is curved geometry. A simple model helps. Imagine a tight rubber sheet. Put a heavy ball on it, and the sheet dips. Roll a small ball nearby. It follows a curved track, not because the big ball yanks on it, but because the sheet itself is not flat. The sun bends space-time around it, the way the heavy ball bends the sheet. Planets move along the paths carved into that shape. This picture is not perfect, but it captures the key point. Change the mass, and you change the shape. Change the shape, and you change the motion. Once you accept that space-time can bend, new shapes become possible in the equations. It can dip and rise. It can make loops. In special cases, it can link separate regions. The equations do not forbid such shapes. In 1935, Albert Einstein and Nathan Rosen found a solution that did exactly this. They were not hunting for fast travel across the galaxy. They were exploring whether particles might be described as structures in curved space-time. Along the way, their math revealed a bridge, two regions of space connected by a throat. Today we call it a wormhole. Back then it was the Einstein-Rosen bridge. The name wormhole comes from a handy picture. Think of an apple. A worm that wants to get from one side of the apple to the opposite side could crawl over the surface. That is the long path. Or it could tunnel straight through the fruit. That is the short path. A wormhole is the tunnel version, a direct route through the inside of space-time, skipping the wide arc across the surface. In the equations, the bridge looks neat and clean. It is symmetric. It matches the rules of general relativity. There was no proof that nature builds such tunnels, yet their appearance in sound equations meant they deserved attention. General relativity had already earned trust by predicting effects later seen by telescopes and detectors. Then came the bad news. The original Einstein-Rosen bridge was not usable. It was unstable. The tunnel would form and then slam shut too fast for anything to cross. Even light, always the fastest traveler, could not make it through. The exact timing depends on details, but the core result is simple. Try to pass through, and the act of passing triggers the collapse. For decades, this kept wormholes in the interesting but not practical drawer. They were allowed by the math, but their lifetime was too brief to matter. To see why this happens, it helps to look at black holes, because the bridge solution sits next to black holes in the landscape of relativity. A black hole begins with a large star that runs out of fuel. The outward push from nuclear fusion stops. Gravity wins. The core falls inward. If the star is heavy enough, nothing halts the collapse. Matter crushes into a region where the density grows without bound. In the equations, that place is called a singularity. Around it lies the event horizon, a one-way boundary. Cross it, and every possible future path leads deeper in. Even light cannot climb back out. For a long time, a black hole sounded like an end point, a place where paths stop. But when physicists solved Einstein's equations more completely, they found an extended picture. In those idealized solutions, the inside of a black hole could be connected through a throat to somewhere else. The math contains the mirror image too, called a white hole. A white hole is like a black hole, run backward in time. Nothing can fall into it. Things can only come out. In that exact, symmetric model, the black hole and white hole are two mouths of a single tunnel. The black side is an entrance. The white side is an exit. This is where hope rises and then falls again. The tunnel exists in the math, but it is exquisitely fragile. Any disturbance, any particle, any bit of light nudges the geometry and causes the throat to pinch off. The passage collapses before the traveler reaches safety. In more realistic settings, where stars form black holes through collapse rather than existing forever, the would-be tunnel never opens in a stable way at all. You can think of it as a bridge that cracks under the weight of even a single footstep. Why is the collapse so quick? Curvature is energy. To keep the throat from closing, you would need something that pushes space-time outward, the opposite of gravity's usual pull. Ordinary matter does not do that. Regular mass and regular light add positive energy. Positive energy makes gravity focus and tighten, which narrows the throat. So the very act of sending even a tiny signal through the passage gives it one more nudge toward closure. This is not a problem with engineering. It is a problem built into the sign of the energy that normal matter carries. These lessons were hard-won. Researchers examined the stability of Einstein-Rosen bridges under small changes. They tested how light rays converge near the throat using tools called energy conditions, simple rules that say, in effect, normal matter behaves like this. Under those rules, the focusing of light and the pull of gravity make closure inevitable. The bridge can appear in the ideal math of a pristine, symmetric universe. It cannot be held open by anything we usually find. The link to white holes adds another challenge. White holes are not known to exist in nature. They are solutions on paper that appear when you mirror a black hole in time. They spit out matter and light, but cannot be entered. If a wormhole demands a white hole on the far side, the model depends on an object we have never observed. That does not mean it is impossible, only that the picture grows less realistic the more you try to tie it to the life story of real stars and galaxies. Still, the idea refused to fade because the logic was clear. If space-time can connect distant regions, and if the connection could somehow be kept open, then the universe would contain paths that beat the usual speed limit without breaking it. You would not go faster than light in your local neighborhood. You would take a shorter route, like the worm in the apple. The challenge is the word somehow. In the simple bridge, there is no support structure. The geometry squeezes shut. To do better, one would need a new ingredient that changes how space-time responds. That is why the original bridges are remembered in two ways. First, they taught us that general relativity admits connections that look like tunnels. Second, they showed that nature does not maintain those connections when only ordinary matter is present. The promise and the failure sit side by side. The math opens a door, then the physics closes it. If a stable passage is possible at all, it will not be built from the same stuff that makes stars and planets. It would require something that bends rules we usually take for granted. Black holes stay at the center of the discussion because they show how extreme curvature behaves and how easily a tunnel can fail. Geometry there can trap light and time, and even a tiny nudge matters. A single photon, the smallest packet of light, adds positive energy and starts the pinch. That means the act of using the tunnel helps to close it. Collapse is not a footnote. It is the main obstacle between a clean sketch and any workable route across the stars. To keep a bridge from vanishing the moment we step on it, the structure would need support that pushes outward where gravity usually pulls in. From that need, the basic mechanism comes into focus. In normal conditions, gravity is attractive. Mass pulls on mass. Anything with energy makes space-time curve inward. Try to open a passage through that curved fabric and it tends to squeeze shut. It is like digging a tunnel in dry sand. Unless you brace the sides, the walls slide inward and close the gap. A wormhole faces the same problem, except its walls are space-time itself, and space-time naturally bends inward under gravity. Keeping the tunnel open would need pressure that pushes outward. In everyday physics, almost everything we know carries positive energy and positive mass. Positive energy makes gravity focus paths together. That is helpful for forming stars and galaxies, but it is bad for an open throat. To resist the pinch, you need the opposite sign. You need stuff that acts as if it has negative energy, so its gravity is effectively repulsive. If such material could line the throat, it could push against the squeeze and keep the shape from closing. Physicists call this exotic matter. It is not antimatter. Antimatter still has positive mass and falls down in a gravitational field. Exotic matter, in the strict sense, would have negative energy density in some region. That would break the usual energy rules that normal matter obeys. No one has found exotic matter as a stable substance in nature. Every particle seen so far carries positive energy. That includes light, which is made of photons. The universe, as we observe it, does not hand us a simple material that props open a wormhole. This sounds like the end of the path, but quantum physics adds a small twist. The quantum vacuum is not truly empty. Tiny fluctuations flicker in and out for short times. In special setups, Those fluctuations can be arranged so that a small region has less energy than the surrounding space. The classic example is the Casimir effect. If you place two clean metal plates very close together in a vacuum, certain waves cannot fit between them. Fewer waves means slightly less energy inside than outside. The plates feel a gentle push together. In simple language, the space between plates acts like it has a small negative energy density compared with the outside region. This hint raises a hard question. Could effects like that hold open a wormhole? The gap is huge between a lab-scale force and a cosmic tunnel. Calculations suggest the amount of negative energy needed for a passage large enough for a person would be vast. It would also have to be arranged with care, placed in the right shape around the throat, and kept there long enough to matter. With today's tools, we cannot produce anything close to that. So, without exotic matter, wormholes remain on paper. The equations allow them, but nature does not supply the ingredients we would need to make them last. The simplest wormhole in the math of general relativity sits inside the same solution that describes a non-rotating black hole. This is linked to Karl Schwarzschild, who found the first exact solution to Einstein's equations in 1916. In that ideal picture, a tunnel connects two regions of space-time. Those regions could be far apart in one universe, or, in principle, they could live in separate universes. The equations do not rule out either picture. Imagine, on paper, two black holes. One could be near our Milky Way's center. The other could be in a distant galaxy. A Schwarzschild wormhole would link their interiors. Enter one event horizon, exit the other. The internal trip could be short even if the outer distance is billions of light years. On the page, this looks like the ultimate shortcut. Then the physics speaks up again. The Schwarzschild wormhole is not traversable. The throat collapses too fast for anything to pass. And even before the throat pinches off, the tidal forces would be deadly. Tidal force means gravity changes noticeably from one part of your body to another. Full feet first toward a strong gravity source, and your feet feel a stronger pull than your head. Near a black hole, that difference can grow extreme. It stretches and squeezes. Astrophysicists call the effect spaghettification. At close range, the atoms themselves would be pulled apart. So even if the tunnel did not snap shut, a traveler would not survive the journey. The bridge exists in the math, but cannot carry traffic. To get a usable passage, the geometry must be different. It must stay open long enough, and the internal forces must stay gentle. For a long time, people left this as a curiosity. The turning point came in the late 1980 seconds when Kip Thorne and his student Michael Morris studied the problem in detail. The spark was a practical one. Carl Sagan needed a scientifically honest way to move a character across the galaxy for his novel. He asked if relativity allowed a believable route. Thorne and Morris did not handwave. They asked what the equations truly permit and what the traveler would feel along the way. They found that a traversable wormhole is allowed by the rules, but only under strict conditions. The throat must be threaded with negative energy density. In other words, it needs exotic matter. That part matched earlier hints. The new step was precision. They wrote down metrics, exact shapes of space-time that have a throat which stays open and produces no killing tides. They computed where the exotic matter must sit and how much is required to counteract the natural pinch. They looked not only at stability but also at comfort. In their models, a traveler could pass Without feeling extreme stretching or crushing, the local acceleration could be kept small. The time to cross could be short, as measured by the traveler's clock. Their results also described how such a passage would look from the outside. You would not see a long tunnel. You would see a spherical opening. Look into that opening and you would see the other mouth's surroundings, not a dark interior. The view would be bent and magnified by the curved path that light takes through the throat. A star field from the far side could appear offset, brightened in a ring, or warped in recognizable ways, much like the lensing seen near massive galaxies. If the two mouths sat in widely separated places, you could peer through and watch a patch of sky that would otherwise be beyond any telescope's reach. Step across the boundary and you would arrive there almost at once. Safety in their design came from two main ideas. First, the throat had to be wide enough. A narrow throat makes tidal forces rise fast. Widen it, and the gradient softens. Second, the geometry had to be arranged so that light rays do not focus too quickly. In technical terms, this means violating the common energy conditions that make light cones tilt inward. Exotic matter does that. It spreads the rays instead of squeezing them, like a gentle defocusing lens. With enough negative energy in the right place, the throat resists collapse. Relativity keeps everything honest. Nothing locally outruns light. The shortcut comes from taking a shorter path, not from breaking the speed limit. In that frame, Morris and Thorne showed that a safe passage is not forbidden by the math, but it needs the right energy pattern. The key is exotic support with negative energy to hold the throat open. They asked how much would be required and found it depends on throat size and the exact curve of the geometry. Early examples needed huge amounts. Later, ideas tried to trim the cost by reshaping the profile, allowing tiny, localized rule bending or using brief quantum pulses. None of this is a build guide. It only shows how finely balanced the system is. Small changes in the supporting stress can keep the throat open or let it fail. The outside would look like a round portal, framing a distant place, warped by bent light. Inside, the ride could be calm if the throat is wide and the curvature tuned. The missing piece is practical, a source and precise control of negative energy at useful scales. On that foundation, the Morris-Thorne design turns the concept into a clear layout. Two mouths, spherical openings in space-time, serve as entrance and exit. They could sit almost anywhere. One near the edge of our solar system, another in a faraway galaxy. A short throat joins them, providing the interior path that beats the long route through normal space. The crucial element is the lining of the throat. It must be supported by exotic matter that pushes space-time outward in that region. Without this support, the geometry caves in and the passage snaps shut. The geometry in these models is spherically symmetric, which means each mouth looks like a sphere from the outside, while the throat acts like a smooth tube between them. Light can pass both ways. Matter can too. There is no event horizon, no one-way barrier like the edge of a black hole. In principle, a traveler could enter, pause in a calm interior, and return the way they came. The interior is engineered, on paper, to be gentle. Tidal forces, the differences in gravity that stretch and squeeze, are kept small by making the throat wide and by shaping the curvature so paths do not focus too quickly. The ride would not feel like falling into a black hole. It would feel like floating in quiet space. The visual experience would be unusual. Approaching a mouth, you would not see darkness. You would see the distant region around the other mouth. At first, it might look like a round window set into empty sky. Move closer, and the window would swell. Stars and galaxies from the far side would sharpen, but the view would be warped, as if passing through a powerful lens. Rings, arcs, and magnified patches could appear, because light bends along curved paths through the throat, cross the mouth, and the change of location is immediate. One moment you are here, the next you are there. Turn around, and the portal shows the place you just left. The strangeness lies in the geometry, not in a violent force. This picture is the closest thing to a practical design allowed by general relativity. It strips away the deadly features of black holes by removing the event horizon and taming the tides. What remains is the central problem. The throat stays open only if exotic matter is present in the right distribution. Classical physics provides nothing with the needed properties. Everything we handle in labs and see in space has positive energy density and focuses gravity, which makes a throat shrink, not expand. Quantum mechanics adds a sliver of hope. In quantum field theory, empty space is not truly empty. It is full of restless fluctuations. Virtual particles appear and vanish in pairs, and fields jiggle even at their lowest energy. Most of the time, these fluctuations average to zero over a region. In special arrangements, the balance shifts. The Casimir effect is the textbook example. Place two clean metal plates extremely close together in a vacuum. Only certain electromagnetic waves can fit between them. Fewer allowed waves means, in effect, a lower energy density in the gap compared with the space outside. The mismatch produces a tiny force that pushes the plates together. The measured force is weak, but it confirms that negative energy density can exist in a limited, localized way. For a wormhole, negative energy density is not a side curiosity. It is the load-bearing element. A civilization able to manipulate quantum fields might try to scale up effects like the Casimir setup, arranging a shell of negative energy around a throat. The demands are daunting. Estimates often reach beyond any power source we can imagine, sometimes by factors so large they sound like fiction. The negative energy would also need to be maintained with precision. If it fades or slips out of place, the throat closes. Even so, the mere fact that quantum theory allows any negative energy at all matters. It says the door is not locked by first principles. Physicists talk about these issues in terms of energy conditions. Energy conditions are simple rules used in general relativity to keep matter sane in calculations. The weak energy condition says that every observer measures non-negative energy density for normal matter. In plain terms, you do not find patches of stuff with less than zero energy. Ordinary fluids, light beams, and fields in classical settings obey this rule. Under those rules, gravity tends to focus paths and close throats. Traversable wormholes need the opposite, so they need a controlled, local violation of the weak energy condition. Quantum fields blur the edges of those rules. As the Casimir example shows, the energy density can dip below zero in a region for a time. That opens a loophole, but it comes with limits. Quantum inequalities set bounds on how negative the energy can be and for how long it can last. These bounds act like speed limits for how much and how long. They prevent someone from creating unlimited negative energy everywhere. If the inequalities are strict, they could block large, stable wormholes by capping the supply of negative energy and restricting its duration. If they are flexible in the right ways, they might permit a carefully balanced throat that stays open long enough for a crossing. The discussion grows technical when you track light rays and geodesics, the paths that light and free-falling objects follow. In normal conditions, bundles of light rays tend to converge under gravity. Negative energy density flips that behavior locally, making rays spread instead. That defocusing is exactly what a throat needs to avoid pinching. The Morris-Thorne metrics are designed so that inside the supporting shell, the focusing equations turn in your favor. The challenge is to realize the required stress energy, the bookkeeping of how much pressure and energy sits in each direction without breaking other physical limits. Design details matter. A wider throat keeps tidal gradients low. Softly varying curvature reduces sharp focusing. Smooth profiles for the stress energy avoid thin, violent layers that could trigger instabilities. Some later studies explored ultra-thin, quantum threads, or shells, where the average energy conditions hold globally, but are violated just enough locally to sustain a passage. Others looked at time-dependent throats pumped by pulses of negative energy, like a heart valve that opens only when the timing is right. Each idea trades one difficulty for another. Less negative energy might require more exact timing. Smoother profiles might demand larger total resources. From the outside, a Morris-Thorne mouth would behave like a compact lens with unusual signatures. It could brighten background objects into Einstein rings, but with distortions not seen around normal masses. The pattern depends on the throat radius and the distribution of supporting energy. Recognizable lensing could be a way to search for such objects in sky surveys, though distinguishing them from more common lenses would be tricky. The lack of an event horizon also changes how matter behaves near the mouth. There is no accretion disk heating up to extreme temperatures just from crossing a one-way surface. Radiation patterns would differ, offering another potential clue for observers. Travel scenarios raise further constraints. To avoid harmful acceleration, the throat's geometry must keep the traveler's proper acceleration low. That is built into the Morris-Thorne prescription by shaping the metric so geodesics remain comfortable. Communication must be considered as well. If light can go both ways, signals can be exchanged across the mouths in real time, limited only by the short throat length. That creates paradox questions once motion or time shifts enter the picture. But the basic traversable design does not require time travel. It only shortens spatial distance by reshaping space-time. The energy bookkeeping remains the central obstacle. Classical matter cannot supply it. Quantum effects can, but only in small doses and for short times, according to what we can calculate today. Scaling from a micrometer-wide plate gap to a meter-wide throat is not a simple matter of multiplying. Fields interact, boundaries reflect, noise and instability creep in. Any drift toward positive energy refocuses paths and starts the collapse. In that sense, a traversable wormhole is less like building a bridge from steel and more like balancing a pencil on its point while gusts of wind pass through the room. The theory side continues to test boundaries. Some approaches in semi-classical gravity study how quantum fields back-react on curved space-time and whether that feedback could support a throat more efficiently than naive estimates suggest. Others examine whether small violations spread over large regions could meet the quantum inequality limits while still providing the needed defocusing. There are also proposals in alternative gravity theories where the effective energy conditions differ, changing the accounting in ways that might help a throat hold its shape. Those models must still match all the precise tests general relativity has already passed. What the Morris-Thorne construction gives us is a clear target: 2 spherical mouths, a short throat, gentle tides, 2-way light paths, and no event horizon. The requirements are stated in plain physical terms: where negative energy must sit, how strong the tidal limits are, how the curvature should be shaped. The unresolved pieces sit on the supply side: how to create, position, and maintain that exotic support within the bounds set by quantum theory and by what we observe. Until a full theory of quantum gravity ties general relativity to quantum mechanics, we cannot fix how much exotic matter nature truly allows. The math points to what is needed, but the final rules live in a theory we do not yet have. Even so, we can sketch what construction would demand if negative energy exists in usable amounts and can be controlled with precision. Two mouths are required. You would either find them or make them. Some ideas in early universe physics suggest that quantum jitters right after the Big Bang could have formed tiny wormholes. These would be microscopic, far smaller than an atom, and useless for travel. If any survived, the challenge would be to enlarge one without letting it collapse. Enlarging means feeding the throat with negative energy. Exotic matter would act like a pressure that pushes outward against gravity's natural squeeze. The process would be like inflating a delicate shell, not a balloon you can overfill and hope for the best. Too much negative energy in one spot could twist the geometry the wrong way. Too little, and the throat pinches shut. The shaping must be active and precise. Stabilizing comes next. The throat needs the right distribution of support everywhere along its length. Engineers would have to map the stress energy, the pattern of energy and pressure that curves space-time and keep it within tight margins. If the support thins in one ring or clumps in another, waves of curvature can grow, and the throat can wrinkle, kink, or tear. These are not cosmetic issues. Small instabilities amplify. A tiny bulge can reflect light and fields in a way that increases the bulge, pushing the system toward failure. Feedback control would be mandatory, with sensors reading the geometry and actuators adjusting the exotic lining in real time. Placement matters. One mouth could stay close to home, perhaps parked in a safe orbit. The other could be relocated. Moving a mouth is not like towing a rock. The mouth is a shaped region of space-time. Accelerating it means changing the energy in and around it, which itself affects stability. Gentle, slow acceleration would reduce stress, but stretches the timetable. High speed would require far more energy and risks upsetting the delicate balance that holds the throat open. A practical concept sometimes mentioned is to attach the external mouth to a ship that applies steady thrust over long periods. The ship does not drag a physical ring. It maintains the conditions that define the mouth while it moves. The trip could take years or centuries, depending on the target and the allowed accelerations. But once placed, the shortcut would connect two fixed locations. Energy costs would be steep at every step, creating or capturing a seed wormhole, expanding it to useful size, stabilizing the throat, moving a mouth, and holding the lining in shape, all demand power. Losses would occur through radiation, field noise, and imperfections. Any real plan would budget for those losses and keep safety margins wide, because a brief lapse that lets positive energy dominate will start the collapse. Relativity adds a twist when a mouth moves. Time does not tick the same for objects that follow different paths. Special relativity says that a fast-moving clock runs slower compared with one at rest. General relativity says that clocks deeper in a gravitational well also run slower than clocks higher up. A mouth that is accelerated to high speed and later brought back will have aged less than the mouth that stayed put. The two ends of a single wormhole can therefore become time-shifted versions of one another. That shift is not a software error, it is how space-time works. A simple setup shows the point. Label the mouths A and B. At first, they sit near each other and are synchronized. You then accelerate B to a high speed, cruise for a while, and bring B back to A. From A's point of view, more time has passed than from B's. Suppose 10 years pass on clocks near A, while only 1 year passes for clocks near B. Place the mouths side by side again. Locally, they share a location, but they do not share a timestamp. A is now at year 2035 inches the surrounding world. B is at year 2026. The wormhole still connects A's interior to B's interior. Step into A in 2035, and you emerge from B into the outside world of 2026. Walk a few steps around B, and you stand 9 years in the past of the place you left. Wait there if you choose, then enter B to emerge from A again in 2035. You now have a loop you can traverse at will. Closed time-like curves are the technical name for such loops. Time-like means the path is one a physical traveler could follow without breaking the speed of light. Closed means the path returns to its starting event. Same place, same time. General relativity allows such paths in several exact solutions. Rotating black holes, called Kerr black holes, contain regions in their idealized form where closed time-like curves appear. Certain cosmic strings and special cosmological models show them too. Wormholes with time-shifted mouths provide a straightforward route. Space is shortcutted by the throat, and the time offset between mouths does the rest. The traveler never goes locally faster than light. The geometry folds the timeline into a loop. Creating the offset does not require extreme speeds if you can use gravity instead. Put mouth B in a region of strong gravity for a while, near a dense object or deep in a potential well, while mouth A stays farther out. Clocks near B will run slow relative to A. Bring B back later, and a time difference remains. Either method, motion, or gravity builds the offset. The size of the shift depends on how long and how strong the speed or gravity difference is. Once a closed time-like curve is available, familiar paradoxes appear in concrete form. Actions at the later mouth can influence events that, in the outside world, are earlier in time. Messages could be sent to avert mistakes, and then the conditions that led to sending the message might never arise. Physical laws do not like contradictions, so theoretical safeguards have been proposed. One is the idea of self-consistency. Events on a closed loop must fit together in a way that avoids logical conflict. Under that rule, you can influence the past, but only in ways that make the loop consistent. Another line of thought invokes quantum mechanics. If the world at small scales follows quantum rules, probabilities might adjust so that contradictory histories are suppressed. A different angle suggests that any attempt to create a loop triggers effects like vacuum polarization or bursts of radiation that destroy the throat or disrupt the needed conditions before a paradox can form. Technical studies follow how stress energy piles up near the mouths as the time offset grows. Many calculations show fields building in ways that threaten the structure, as if the physics itself resists a working time loop. Whether that resistance is absolute or just a warning in certain models is still unclear. The answer likely hinges on quantum gravity details we do not yet know: how quantum fields behave on fast-changing geometries, how horizons and throats back-react when energy spikes, and whether quantum inequalities tighten as loops try to close. For now, the requirements stay plain. A traversable throat needs negative energy. Moving a mouth creates a time shift. With a large enough shift, paths through the tunnel can loop a traveler's world line back to earlier events, and then cause and effect must be handled with care. Those puzzles have concrete names. The classic example is the grandfather paradox. What if you step through and prevent your younger self from taking that step? Change the past, change the future, until the links fold back on themselves. Go back before your parent is born and your grandfather dies because of your action. Then your parent never exists. Then you never exist. Yet you were the one who went back and caused the event. The chain cannot settle into a single, stable story that holds every link at once. One way out is the idea of consistency. Physicist Igor Novikov framed it this way: the laws of nature forbid contradictions. If a closed loop through time exists, only actions that fit a self-consistent history can happen. Try to make a change that would block your own trip, and something gets in the way. The tool misfires, you slip, the timing shifts, or someone else intervenes. None of these need to be magical. They are ordinary events that, taken together, keep the timeline free of logical knots. You have freedom to act, but not freedom to create a paradox. Some find this neat, and some find it troubling, since it looks like destiny in disguise. Your trip back was always part of the record, and every choice you make there was always baked into the world you left. Another route is the many worlds view from quantum mechanics. In that picture, reality branches. Each outcome lives on its own track. Travel to the past and change an event, and you do not delete yourself. You enter a branch where your action is part of the story and where your younger self may never be born. The original branch carries on, unchanged. This avoids contradiction at the price of a vast number of parallel histories. Some researchers accept the trade because it makes the math clean. Others see it as a heavy cost with no direct test to settle the question. A third answer says backward travel is blocked in practice. This idea is known as chronology protection, a term Stephen Hawking used. The claim is not that we can prove a band today, but that hidden limits in the laws of physics step in whenever a loop tries to form. The would-be time machine either collapses or becomes so unstable that it cannot operate. The safeguard might come from quantum fields, from gravity, or from their union in a full theory we do not yet have. Quantum behavior near a would-be loop is the pressure point. In flat space, a single photon is simple. Near a wormhole with a time shift, even one photon can interact with a version of itself from the future. The future photon nudges the past one, which changes the future one, which changes the past one again. The feedback can pile up. In simple models, the energy density near the mouths grows without bound, like sound squeal in a microphone loop. That rise drives the geometry toward a singular behavior and can tear the structure apart. In that view, nature protects chronology not by decree, but by letting ordinary quantum rules create runaway effects that stop the loop. There is also a softer version of the same idea. Instead of a blow-up, small disturbances accumulate in a way that pinches the throat, closes the tunnel, or scrambles the timing enough to break the closed path. Each attempt to set up a neat loop adds stray radiation and noise. Those additions change the conditions that allowed the loop in the first place. The closer you get to a paradox-ready state, the more the system fights back. Through back reaction, the mutual push between fields and space-time. Not everyone agrees that quantum fields always destroy the loop. Our math is strongest when space-time changes slowly and when energies stay modest. A wormhole turned into a time device is neither. The geometry shifts quickly. Fields reflect many times. Approximations break down. Some studies suggest that with the right arrangement, the feedback can settle into a consistent pattern rather than blow up, a kind of fixed point where every influence fits without contradiction. In such a case, the traveler's actions are not free to vary at will. They slide into the values that make the loop coherent. This echoes the consistency idea, but framed in quantum terms, with probabilities adjusting so only non-paradox paths have weight. There are technical tools that try to fence the problem. Quantum inequalities, for example, limit how negative energy can be and how long it can persist. They also constrain how fields can behave along paths that threaten to close in time. If these bounds are strict enough, they cut off the fuel needed to keep a loop open. If they leave room, then carefully shaped pulses might support a throat without runaway growth. Which side wins depends on details we cannot yet compute with full confidence. Even the background matters. A rotating black hole described by the Kerr solution twists space-time around it. In its idealized core, closed time-like curves appear in the equations. But real black holes form from collapsing stars and sit in messy environments. Add quantum effects, and the tidy regions where loops would exist may be replaced by turbulent zones where no stable path survives. Cosmic strings and other exotic defects tell a similar story. The exact solutions allow loops. Realistic settings add noise and limits. Wormholes with time-shifted mouths make the setup easy to picture. A finite time offset is enough. Send a particle through the short throat, bring it out earlier, let it interact with its former self, and repeat. Whether this creates inconsistency, a stable, self-consistent loop, or a breakdown depends on how quantum fields share information with the geometry. Calculations in semi-classical gravity, where quantum fields live on a curved background, and their average effects bend the background in return, hint at stress buildups near the mouths. But a full quantum gravity theory would be needed to say how those buildups end, with collapse, with a stable balance, or with something we have not yet named. All of the proposals share a common structure. Paradoxes arise when a path lets information circle back and change the conditions that created it. Fixes either block the loop, make the loop self-consistent, or split histories so that no single story must carry both sides of a contradiction. The math of general relativity leaves the door open to loops. The rules of quantum theory push back through limits on energy, feedback effects, and the probabilistic nature of events. Which effects dominate depends on scales, on how strong the fields are, on how fast the geometry changes, and on how closely a real setup would match the ideal models used in thought experiments. Some ideas point to wormholes that form on their own. In the first tiny fraction of a second after the Big Bang, space-time was hot and restless, quantum fluctuations were large, and geometry itself was not smooth. At those scales, sometimes called the Planck scale, the smallest meaningful scale in physics, space-time may behave like foam, busy, uneven, full of brief structures that appear and vanish. In that foamy state, tiny wormholes could have popped into existence for moments and then faded. They would be far smaller than an atom and would not last, but they would be part of the natural noise of the early universe. A few theories add a twist. Right after the beginning, the universe may have gone through a phase of rapid expansion called inflation. Inflation stretches distances by huge factors in a very short time. If a microscopic wormhole formed just before or during this phase, the expansion might have pulled it to a larger size. Most would still disappear, yet a rare set might survive and grow to macroscopic scales. If any did, they could still exist now, scattered through space like hidden doorways. They would be rare and hard to notice, but not forbidden by the math. Finding one would be difficult. Black holes reveal themselves by the way they trap light and by the motion of stars and gas around them. A wormhole mouth does not need an event horizon. From far away, it could act like a compact mass that bends light without swallowing it. Astronomers call this bending gravitational lensing. A mouth in front of a distant star could warp the star's image into arcs or rings. The challenge is that other objects, stars, black holes, even whole galaxies, also lens light. The pattern from a wormhole might have subtle differences, such as how strongly it magnifies background sources, how the ring brightens, or how the distortion changes with time as the alignment shifts. Separating that unique pattern from the crowded sky would require careful modeling and long, precise observations. There is also the idea that wormholes could live inside black holes. The center of a black hole in classical general relativity is a singularity where the theory breaks down. Some proposals suggest that quantum effects replace the singularity with something else, such as a tunnel that continues to another region of space-time. In that picture, the entrance is the black hole's event horizon, and deeper inside sits a throat that leads elsewhere, possibly to a different place in this universe, or even to another universe. Such a passage would be a one-way route. Crossing the horizon prevents any signal from returning, so no measurement outside can confirm what lies within. The idea cannot be tested directly with present methods, but it remains an active area of research because black holes are where gravity and quantum rules meet most sharply. If natural wormholes exist anywhere, there might be many of them, a kind of hidden network linking distant places. Most would be quiet. Some might interact with their surroundings in ways that could be noticed. This leads to practical search strategies. Gravitational lensing is the first tool. Surveys already scan the sky for lensing by dark matter and galaxies. A wormhole lens could show a different symmetry or brightness profile compared to a normal mass of the same apparent strength. For example, a mouth without an event horizon should not produce the same shadow or photon ring structure as a black hole. Its light paths could create characteristic rings with different thickness or brightness across the ring, depending on how the throat bends light. Repeated measurements over time, as stars move and alignment changes, could reveal telltale shifts that models of ordinary lenses cannot match. A second tool is to watch for signs of exotic support. If a traversable mouth is held open by negative energy density, fields near the throat may behave in unusual ways. That could include radiation with distinctive spectra or patterns of high-energy particles. A steady, narrow band glow is unlikely. More plausible would be faint, broadband signals shaped by the geometry, or brief flares when matter from the environment brushes the mouth and some fraction of it is redirected or amplified. Gamma rays or fast particles from a point-like source with no visible counterpart could be a hint, though many astrophysical objects also produce such signals, so follow-up tests would be needed. Orbital anomalies provide a third approach. A wormhole mouth acts, in part, like a compact mass, but its curvature can differ from a simple black hole of equal mass. Stars near the galactic center already serve as precise test masses. Tiny deviations in their orbits, extra precession, unexpected shifts in timing, or changes in velocity not explained by the known mass could point to a compact object with unusual structure. Similar logic applies to planets, pulsars, or binary stars if a mouth sits nearby. High-precision timing, especially with pulsars, can detect gravitational tugs smaller than anything seen by optical telescopes. There is also the possibility of matter flow. In some models, gas, dust, or even radiation could fall into one mouth and emerge from the other. The source might look like a sudden outburst with no buildup, as if energy appears from nowhere. A jet-like feature without a feeding disk or a burst that repeats with a pattern set by motions on the far side, would be unusual. Radio telescopes, X-ray instruments, and neutrino detectors all watch for transients, short-lived events that flare and fade. A subset of these events could, in principle, be due to hidden mouths. Matching events across different parts of the sky and across different wavelengths could build a case, especially if timing and brightness fit models of a two-mouth system. Each of these signals must compete with more ordinary explanations. Galaxies lens background light. Neutron stars and black holes produce bursts and jets. Dark matter clumps tug on orbits. The case for a wormhole would rest on patterns that resist every standard model, and on a set of observations that fit together in one design. A compact, horizonless object with the lensing of a mass, the radiation quirks of exotic support, and the dynamics of a geometry that is not quite a black hole. The practical side is improving fast. Sky surveys now map billions of galaxies and millions of strong or subtle lenses. Telescopes that see in radio, optical, X-ray, and gamma rays run wide field and watch for fast transients. Pulsar timing arrays measure tiny timing shifts across years. Gravitational wave observatories listen for ripples from compact objects as they merge. None of these were built to find wormholes, but all of them could, in the right circumstances, catch the edge of one. A strong case would likely need multiple instruments. A lensing pattern that looks wrong for a black hole, a missing shadow where one should be, a peculiar spectrum, and motion in nearby stars that matches a horizonless mass. Natural or built, large or small, wormholes sit at the boundary of what current theories allow. Early universe foam offers one path to small, fleeting tunnels. Inflation could, in rare cases, make a few large enough to matter. Black hole interiors propose another path, replacing a singular center with a bridge. Detection, if it comes, will not be a single photograph or single burst, but a pattern that repeats across methods. Until then, the search narrows what is possible and refines how a wormhole would differ from every other compact object the sky has to offer. Astronomers already watch the sky for brief events that flare and fade. Most turn out to be supernovae, merging stars, or jets from black holes. A few resist easy labels. Those outliers are logged, modeled, and compared across telescopes to see whether any match the odd patterns a wormhole might leave. No confirmed wormhole has been found, but the search is young, and each generation of instruments brings sharper images, faster timing, and wider surveys. The path forward is steady observation, not a single dramatic test. A different thread links wormholes to quantum entanglement. Entanglement is a tight correlation between particles. Prepare two particles in a shared quantum state. Separate them by a great distance, and measurements on one still line up with measurements on the other in a way that statistics predict. No signal races between them. The match comes from how the joint state is built. Einstein disliked the idea, calling it spooky, yet careful experiments show it is real and repeatable. It sits at the core of quantum technology, from secure communication to early quantum computers. The surprising link came from a proposal that ties two famous ideas together. The Einstein-Rosen bridge is the textbook wormhole that appears in certain solutions of general relativity. The Einstein-Podolsky-Rosen paper is the classic argument that pushed physicists to clarify entanglement. Put them side by side, and you get a slogan: ER equals EPR. The slogan is not a numeric equation. It is a claim about structure. It says that entangled systems may be connected by non-traversable wormholes at a deep level of description. Nothing, travels through these links. You cannot send a message or a person. The connection shows up in the math as a geometry that mirrors the correlations of the quantum state. Taken seriously, the idea suggests a fresh way to think about space-time. The smooth fabric we see at large scales could emerge from a web of entanglement at tiny scales. If you could zoom in far enough, you would not find a continuous sheet, but a network of quantum links, like threads that, woven together, act like space. Stronger patterns of entanglement would make geometry that is more tightly connected. Weaker patterns would make regions that sit farther apart. In this view, wormholes are not rare add-ons. They are the shadows of entanglement patterns that never allow travel, but do shape how space holds together. This picture also touches a long-standing puzzle about black holes. When matter falls in, its details, its information seem to vanish behind the horizon. Quantum rules say information cannot be destroyed, even when scrambled. General relativity says once past the horizon, no signal returns. That tension is the black hole information paradox. If ER equals EPR is right, the quantum entanglement between a black hole and the radiation it emits could be represented by wormhole-like connections in the full theory. Those links would not let anything escape faster than light, but they could encode how information is preserved across the whole system, reconciling the bookkeeping in a way that respects both gravity and quantum mechanics. This is an active research area, not a closed case, yet it shows how wormhole ideas can guide work on problems that seemed unrelated. There is another horizon for speculation: other universes. Some models of cosmic inflation suggest that expansion did not happen once and stop. Instead, it can continue in other regions, creating many bubble-like universes with different conditions. Our universe would be one bubble where inflation ended and cooled into galaxies and stars, while elsewhere it continues or ended with different outcomes. If such a multiverse exists, nothing in the simple geometry of a wormhole forbids connecting separate bubbles. A tunnel might link our space-time to a region with different constants or particle properties. Crossing would not only move you somewhere else, it might move you into a place where the rules that shape atoms and stars are not the same. Evidence for other universes is absent. The idea comes from extending equations beyond what we can test, then asking what follows if those extensions hold. Within that frame, wormholes become natural bridges between spaces, rather than just shortcuts within one. A related thought is that what looks to us like a black hole might lead, beyond its horizon, to a region that functions as a white hole in another spacetime. Matter and energy that fall in here would pour out there. From that other side, the object would look like a source, not a sink. This exchange keeps to the rule that nothing climbs back out through the horizon on our side. It simply reframes where the paths go once they pass the point of no return. None of these links are testable today. They are maps that show how different ideas might fit together. Entanglement is measured in the lab. Black holes are observed across the sky. Inflation has support from cosmic background data, though not in a way that proves eternal inflation. The bridges between these topics live in theory. Progress comes from tightening the matches between models and measurements, better observations of black hole environments, sharper tests of how information behaves in quantum systems, and refined predictions for lensing and radiation that would separate wormholes from ordinary compact objects. Practical searches continue on several fronts. Wide-field surveys catch sudden brightening and fading that might reveal unusual lenses. High-resolution imaging of compact objects looks for shadows and rings that match black hole predictions. Any persistent mismatch would be a clue. Pulsar timing watches for tiny tugs that suggest nearby masses with non-standard geometry. High-energy observatories catalog bursts and jets, looking for patterns that fit no known engine. Cross-checks between instruments matter because a true outlier should look odd in more than one way at once. On the theory side, the ER equals EPR thread pushes researchers to think of geometry and quantum states as two views of the same thing. Tools developed for quantum information, the study of how information is stored, moved, and protected, now appear in gravity research. Ideas like error-correcting codes, which keep data safe even when parts of a system fail, turn up in models where space-time itself behaves like a code that weaves local physics from deeper, non-local links. In those models, a wormhole is not a hole through a pre-existing stage. It is a pattern in the stage itself. If nature follows anything like that plan, then entanglement is not just a curiosity of particles. It is the ingredient that holds large-scale structure together. A small, non-traversable wormhole would be the geometric face of a simple correlation. A large, traversable wormhole, if it can exist at all, would require extra ingredients, like negative energy, to change the rules locally. The first is common and quiet. The second is rare and demanding. Distinguishing them is the difference between seeing how the world is built and making a machine that exploits a loophole. As instruments improve, the search space widens. Telescopes that watch millions of stars, night after night, make it easier to spot lensing with unusual patterns. Arrays that time dozens of pulsars let us feel the gravitational pull of objects we cannot see. Detectors that listen for gravitational waves tell us how compact objects move and merge, offering a new way to test whether any behave unlike black holes and neutron stars. Each method places constraints on what a wormhole could look like without having shown up already, narrowing the options and pointing to where to look next. Not just shortcuts across space or devices that shift clocks, but bridges that could link separate realities. Turning that into hardware runs into a wall of engineering. The first obstacle is the need for negative energy. A traversable throat must be supported by a region where energy density is below zero, so gravity defocuses rather than focuses. No laboratory has produced bulk negative energy, and every known particle carries positive energy. Even if a mechanism existed, scaling from tiny quantum effects to a human-sized throat would likely demand resources on the scale of planets or stars. Estimates vary with design, yet many land in ranges that eclipse any power system we can plausibly build. Precision is the next obstacle. The supporting energy cannot be dumped in loosely. It must be shaped so that the throat's curvature stays smooth, the tidal forces stay small, and light rays avoid focusing. Small errors create instabilities that grow, like ripples that reflect inside a cavity and amplify. Holding shape would require sensors that read geometry in real time and actuators that adjust the stress energy profile on demand, all while avoiding noise that tips the balance toward collapse. Construction raises its own set of problems. If tiny wormholes exist in quantum foam, they would be smaller than atoms and short-lived. Capturing one and enlarging it would mean feeding negative energy without letting positive energy leak in and trigger a pinch. Building from scratch is no easier. You would need to concentrate intense energy in a small region to sculpt curvature into a bridge rather than a black hole. Then thread the throat with the exotic support before the structure snaps shut. Each step has failure modes that destroy the device or turn it into a one-way trap. Long-term stability also matters. External disturbances, passing stars, gas flows, radiation fields would tug on the geometry. Internal fluctuations in the supporting fields would drift. A practical system would need continuous monitoring, damping, and correction. Without that, small drifts become runaway changes. Safety adds further constraints. A mouth placed in a planetary system could lens light, alter orbits, or channel radiation. Interactions between the lining fields and ordinary matter might produce unexpected particles or bursts. Any design must show that it contains and manages these effects before traffic begins. If a civilization mastered all of this, the payoff would be large. Two fixed mouths make instant links between distant places. A network becomes a transportation grid, a communications backbone, and a safety net. Regions threatened by supernovae or gamma-ray bursts could be evacuated. Isolated systems could exchange medicine, tools, and knowledge on human timescales. Trade routes would no longer follow the slow arcs set by chemical or fusion rockets. They would follow geometry someone maintains. Other concepts chase similar goals. The Alcubierre idea reshapes space-time into a moving bubble. Space contracts ahead of the bubble and expands behind it, while the interior stays flat. From outside, the bubble crosses distances faster than light. Inside, the crew coasts in free fall. The math sits within general relativity, but the requirements echo the wormhole story. Negative energy is needed to create and sustain the bubble's walls. Early estimates asked for energy beyond the mass energy of the observable universe. Later refinements reduced the budget by changing the bubble's shape and thickness. But even optimistic numbers remain far beyond our reach. Practical issues stack up. Forming the bubble may be unstable. Edges that are too sharp promote quantum noise and back reaction. A ship cannot steer or send signals outside the bubble by ordinary means, since light inside follows the local flat geometry, and the bubble walls isolated from the exterior. Arrival could be hazardous if the bubble accumulates particles and fields in front and releases them as a damaging blast when it decelerates. Proposals to mitigate these issues include tapered walls, staged ramps in and out of warp, and sequences of smaller bubbles that hop in a chain rather than one large continuous region. Some ideas suggest using strong, natural curvature near compact objects to lower the startup cost, though that introduces its own risks. These variations do not change the central fact. Negative energy appears again as the enabling ingredient. Without a reliable way to generate and control it in bulk, both traversable wormholes and warp bubbles remain designs on paper. If future physics finds roots around quantum limits, the engineering would still demand levels of control we do not currently have, field shaping at high precision, fault-tolerant systems that correct geometry in real time, and power sources that run far beyond fusion. Even so, mapping the obstacles has value. It clarifies which measurements matter now. Experiments that probe quantum energy bounds test how much negative energy can exist, and for how long. Astronomical observations that distinguish horizonless compact objects from black holes teach us what stable, strong curvature structures look like in nature. Advances in precision timing, high-energy detectors, and gravitational wave astronomy build a baseline that any future anomaly must clear to be persuasive. The strategic view extends beyond transport. A single mouth near every major habitat would change how societies plan for rare risks. Evacuation paths would not depend on launch windows or propellant stocks. Supply chains could route around damaged regions. Knowledge could move without delay, letting medicine and engineering propagate quickly. The same links, if misused, could spread hazards as well, which makes governance and safety protocols as central as physics. Alternatives crop up in other corners of theory, engineered cosmic strings that pinch space into shortcuts, wormhole-like solutions in modified gravity that relax energy conditions, proposals that use quantum teleportation protocols across pre-existing microscopic links. Each idea trades one difficulty for another: materials that have never been seen, deviations from general relativity that must still pass all precision tests, or reliance on entanglement that cannot carry classical information faster than light. Sorting these options requires the same discipline: list assumptions, match predictions to data, and keep only what survives contact with observation. If travel that ignores interstellar distance is ever realized, it will come from controlling geometry rather than pushing a vehicle through empty space. That control depends on energy sign and distribution, on stability under noise, and on the ability to measure and correct faster than instabilities grow. In that light, the path from speculative math to technology runs through quantum field constraints, precision metrology, and power systems that exceed anything in use today. Concepts like wormholes and warp bubbles mark the far edge of what current theory permits, and sketch how a mature civilization might knit distant places together. Those same concepts feed a broader question about cosmic silence. If such tools are possible, and the rewards are as large as they seem, why is space so quiet? The question of why we have not met anyone else sits beside the ideas above. The Fermi paradox asks why a galaxy with so many stars, so many planets, and so much time shows no clear sign of technology beyond our own. The Milky Way holds hundreds of billions of stars. Many have planets. A fair share sit in regions where liquid water could exist. If life starts on even a small slice of those worlds, and if a fraction of those biospheres produce intelligent tool users, there should be plenty of chances for signals, probes, or structures we could notice. Yet radio surveys are quiet. Nearby stars do not show obvious engineering. Spacecraft that wander the outer solar system find rocks, ice, and dust, not visitors. One answer uses wormholes to explain the silence. If a civilization can build reliable mouths and throats, slow starships are not worth the risk. You do not cross the dark between stars. You step from one region to another. Travel leaves little trace for outside observers. No long radio chats are needed, because a link joins places directly. No shiny megastructures encase stars, because energy and matter can be moved on demand through compact portals. From our point of view, nothing passes through local space. A traveler appears where the mouth is, spends no time in transit we can track, and departs the same way. In that picture, advanced societies could be common and active, but their main roads sit outside our detection methods. This still leaves us in an early phase. We send robotic probes to the outer planets. We plan for crewed trips to Mars. These are meaningful steps, yet they remain local. If a network of stable mouths were possible, the map of what is reachable would change at once. Star systems would become neighbors. The barriers of distance would be replaced by the barriers of maintenance and governance. Without such tools, a young species stays tucked near its star, looking out and listening. There is also the plain possibility that wormholes that carry traffic cannot exist. If quantum rules cap negative energy too tightly, or if back reaction always ruins attempts to keep a throat open, then every civilization faces the same speed limits we do. In that case, the paradox remains. The quiet might have other causes. Life is rare. Intelligence is rare. Technology burns itself out. communication habits are unlike ours, or signals fade before they cross interstellar space. Wormholes solve the travel problem for those who have them, but they also hide activity from those who do not. The idea has lived in fiction for a long time, which is part of why it is familiar. Stories use wormholes to move characters quickly and to bring distant places onto the same stage. Sometimes the science is loose, and the tunnel behaves like a doorway with no cost. Sometimes the treatment follows real equations. A well-known example is a film that worked with Kip Thorne's models to render a mouth as a sphere that shows the other side. The halo and lensing arise from bent light paths, not from glow or magic. When characters draw near, the distant scene fills the frame and warps, as a true lens does. Effects teams used real math to shape those images. The story also uses time differences that come from relativity, letting hours in one region match years elsewhere, which is a real consequence of gravity and motion. Other series imagine stable, natural portals that anchor trade routes or military choke points. These often set aside the need for negative energy or the risk of collapse, but they pass along the core idea that space can have shortcuts. More than a few researchers first met these concepts through books and shows, and later learned the limits and the care that the real physics demands. The study of wormholes pushes on deep questions in physics. To know whether stable passages are allowed, we need a framework that handles both curved spacetime and quantum fields in full detail. General relativity works for planets, stars, and galaxies. Quantum mechanics works for atoms and particles. Each theory has passed hard tests, but they disagree in places where both should apply, such as the center of a black hole or the first fractions of a second after the Big Bang. A theory of quantum gravity would join them. It would tell us how energy conditions are modified by quantum effects, how back reaction proceeds when fields are intense, and whether closed time-like curves can be formed or are always blocked. Several lines of work try to build that joined picture. String theory replaces point particles with tiny vibrating loops or segments. Different notes on a string are different particles. Geometry in this view is part of the same system as the strings themselves, not a fixed stage. Wormhole-like structures appear in string setups as connections between regions in the full, higher dimensional space. Because strings carry both matter and gravity, this approach can model how quantum states and geometry talk to each other. It also connects to the holographic principle, where certain gravitational systems are exactly equivalent to quantum systems, without gravity living on a lower dimensional boundary. In that duality, links between parts of the quantum system map to connections in the bulk geometry, and statements like entanglement builds space-time become precise. Wormholes then look like geometric images of correlations. A different approach, loop quantum gravity, tries to quantize geometry itself. Space is not smooth. It is built from discrete loops or spin networks. Areas and volumes come in tiny quanta. Near Planck scales, the smooth fabric breaks into a granular structure. In such a setting, the singularities of classical relativity can be replaced by bounces or finite structures. Short connections at very small scales are part of the network, and some models suggest that the early universe foam could include wormhole-like links. Whether these can be scaled up or remain at tiny sizes is an open problem, but the framework gives a concrete way to discuss what space is made of. The holographic principle adds more tools. It states that all the information inside a region with gravity can be represented by degrees of freedom on its boundary, somewhat like a three-dimensional scene encoded on a two-dimensional surface. This idea grew from the study of black hole entropy and has been formalized in certain cases. In those models, entanglement in the boundary theory controls the connectedness of the bulk geometry. Break entanglement, and regions pull apart. Increase it, and regions fuse. Non-traversable wormholes in the bulk correspond to particular patterns of entanglement on the boundary. This gives a laboratory for testing ideas like ER equals EPR, and for asking how information moves in systems that look like black holes. All of these frameworks are incomplete, and none has yet delivered a final answer about large, safe, traversable wormholes. They do, however, sharpen the questions. They tell us what must be calculated: the exact stress energy needed to support a throat, the quantum limits on negative energy, and how long it can last, the stability of a passage under noise, and the signatures that would distinguish a horizonless compact object from a black hole in observations. They also suggest measurements to make now: precise imaging of black hole shadows and photon rings, surveys for unusual lensing patterns, timing arrays for tiny gravitational tugs, and experiments that probe quantum vacuum effects and the bounds that govern them. The Fermi paradox stays in the background as a test of our expectations. If advanced life is rare, quiet, or self-limiting, the empty sky is no surprise. If advanced life is common and long-lived, then either they avoid contact, hide well, stay local, or move in ways we cannot see. Wormholes offer a mode of movement that leaves few traces and no obvious radio chatter, which fits one branch of answers. A ban on traversable throats would push us to other branches. Either way, the same instruments and theories that would reveal a wormhole also build the larger picture: how gravity and quantum rules fit together, how information survives in extreme places, and how to read subtle marks in light and motion that tell us what kind of compact objects populate the universe. Whether a wormhole will ever be seen depends on what nature allows and on how well we can measure. If tiny tunnels formed in the early universe and a few survived, their presence could show up through subtle lensing. A compact mouth bends light like a mass, but the pattern it makes on a background star or galaxy is slightly different from a black hole's shadow and ring. With long, careful monitoring, advanced telescopes could separate those patterns and flag candidates. Another window is gravity's own waves. Colliding black holes already ring the detectors we have. A wormhole, if it vibrates or interacts, could leave a waveform with echoes or delays, unlike standard mergers. A repeatable, odd signature would count as indirect evidence, and it is the kind of signal present surveys can at least search for. If the deep link between entanglement and wormholes is right, then microscopic, non-traversable bridges could already be part of routine lab work. Entangled photons and atoms are made every day. In that view, the links are not travel routes. They are geometric ways of describing quantum bonds. Future tools that map quantum states with more detail, better tomographic methods, cleaner control of many body systems, might let us test whether those bonds have gravitational analogues in controlled models. Even a small, artificial system that mirrors the math would be a step toward checking the idea that space-time structure grows from entanglement. Building a macroscopic wormhole would be obvious once achieved, yet the engineering gap is the largest of all. Negative energy on demand, field control at extreme precision, power sources far beyond fusion, and stability management would be required. That places construction in the distant column, even for a very advanced culture. For now, wormholes remain in theory, clear in equations, unconfirmed in the sky. Their status still matters. A possibility allowed by sound physics expands the range of what may be real, and it guides what signals to seek. These ideas carry broad consequences. They force clear statements about space, time, and cause. Work on wormholes sharpened the study of black holes, helped frame questions about information loss, and inspired links like ER equals EPR that join gravity and quantum theory in new ways. They also encourage checks on the limits of negative energy through quantum inequalities and strengthen the case for proposals like chronology protection, which would stop closed time loops from forming in practice. Even if a large, traversable tunnel never exists, the math and the measurements shaped by the search refine our picture of spacetime. If wormholes are part of nature, the universe is more connected than it looks. Regions far apart could be near in the underlying geometry. Access to different times could, in principle, be encoded in the shape of that geometry. In the more speculative extensions, entirely separate spacetimes could be linked. If wormholes never exist outside theory, that result is also informative. It would say that certain patterns of cause and effect are protected, that negative energy is bounded too tightly to prop open a throat, and that some shortcuts are barred at a basic level. Either outcome answers a real question about limits. Distance has always set the scale of our plans. Even the closest star is over 4 light-years away, well beyond any ship we can build today. A usable wormhole would remove that barrier in one move. A person could step from one mouth to the other, and the travel time would be set by the throat length, not by the miles around it. The value would not be speed for its own sake, but the reach it grants to research, medicine, rescue, and collaboration. The change in mindset would be as large as the change in method. The dream itself has use. It keeps attention on what would have to be true for such travel to work, and on what evidence could show whether those conditions ever occur. It turns vague hope into testable questions. Do horizonless, compact lenses exist? Do gravitational wave echoes appear? How negative can energy be for how long? How do quantum systems that model gravity handle information and causality? Answers to these define the boundaries of what can be built, even if the final answer is not this way. At a deeper level, wormholes test the edges of realism. We picture space as 3 dimensions laid out like a quiet stage, and time as a one-way line. The core physics already tells us that this picture is limited. Curvature changes the stage. Motion and gravity change the rate at which clocks tick. Wormholes push that lesson further. If a short path exists where the long path dominates our view, then distance is not only about miles, it is about the structure those miles live on. If time shifts can be engineered between mouths, then before and after become features of a path, not absolute labels. Questions that spill out from that are not just academic. If geometry can be shaped, what counts as a location? If a path loops back, how is a record kept without contradiction? If the same event can be part of different large-scale orders depending on route, what is the minimal way to state cause and effect that survives all paths? Physics answers with models and tests. Philosophy checks the clarity of the terms. Each helps the other when the topic is this strange. The practical search keeps moving. Detectors gain sensitivity. New interferometers listen for smaller ripples. Sky surveys expand and speed up, catching more transients and resolving finer lensing details. Pulsar timing arrays add years of data and more stable clocks. Quantum platforms with dozens or hundreds of controllable elements act as test beds for ideas that tie information to geometry. None of these guarantees a wormhole will be found. All of them improve our ability to tell a wormhole-like signal from the many ordinary processes that can mimic one part of its pattern. A steady gain in knowledge, is the common thread. Even a null result tightens bounds. If no exotic lens shows up in a given mass range, if no echoes appear above a given signal to noise level, if negative energy is restricted to certain sizes and durations, then models adjust. Those adjustments feed back into telescope designs, data pipelines, and theory. Over time, the space of possible wormhole signatures shrinks toward what is most plausible. The same work informs how a long-lived civilization might plan. If a network of mouths can exist, its design would weigh stability, safety, and governance as much as physics. Where to place portals, how to meter traffic, how to monitor stress and prevent misuse. These are engineering and social questions that follow from the physics. If such a network cannot exist, planning turns to long voyages, cryogenic storage, robotic precursors, and slow, secure growth away from the home star. Either way, the route forward rests on honest limits and on the tools that test them. A final cluster of questions sits at the edge of current research programs. How does information escape a system that looks like a black hole without breaking quantum rules? How do quantum error-correcting structures map to bulk geometry? And can that map be checked in tabletop systems? How tight are quantum inequalities in dynamic spacetimes, not just in static models? What, if anything, replaces singularities when quantum gravity is treated fully? Each of these touches the same core issue: what spacetime is made of at small scales, and how its large-scale behavior emerges. Looking out at the sky, it is natural to ask whether bridges exist in the wild. Looking inward at the equations, it is natural to ask which bridges can be sustained without contradiction. Between those questions lie measurements we can make now and theories we can refine now. Bit by bit, those will say whether tunnels through space-time belong only to math or also to the world we measure, and which signals count as the clean marks to watch for in the data that arrives night after night. Questions that sound simple carry wide consequences. If other minds exist, wormholes change what near and far mean. A society using mouths and throats would not sweep past our telescopes with radio beacons or bright engines. It would move by stepping across geometry, leaving little for us to track. If there are no other minds, the same tools become a way to carry life outward, planting habitats in places that normal ships would never reach. The puzzle about time sits beside this. Closed time-like curves would make before and after path dependent. Time would still measure change, but the map could include loops and shortcuts, the way space already includes tunnels and bridges. Far futures raise a third issue. When stars fade and galaxies drift apart, narrow links could preserve contact and provide exit routes from dim regions. A small, stable mouth could be a lifeline when local energy runs low. No one field owns these questions. They return us to first principles. General relativity says space-time is a shape that responds to energy and momentum. Quantum theory says the world comes in discrete packets, with uncertainty and entanglement built in. Wormholes press on both stories at once, pushing us to ask where cause, information, and geometry meet. They do not promise easy answers. They do encourage better ones. Even without a single observation, the idea has left marks. It drove studies of energy conditions and the limits on negative energy in quantum fields. It sharpened work on how information moves in systems that look like black holes. It inspired programs that linked geometry to entanglement, turning slogans into equations in controlled models. Outside research, the image of a round window showing a far place, has become a way to talk about distance, time, and choice. Stories took the tunnel as a stage device. Careful films used real equations for lensing and tides, and many viewers first met the physics there before finding the papers behind it. Answers about existence rest on the same math. Einstein replaced a fixed stage with a fabric that bends. A mass curves spacetime. Objects follow the curves. The field equations tie curvature to stress energy through 10 coupled relations. Most exact solutions are hard-won. A non-rotating mass gives the Schwarzschild geometry. Add rotation, and the Kerr solution appears. Fill the universe with a uniform fluid, and you get the expansion encoded by the Friedmann-Lemaitre-Robertson-Walker family. Each teaches a different lesson. Each also hides surprises. In the Schwarzschild picture, the extended, ideal form contains an Einstein-Rosen bridge. It links two regions through a throat that pinches off too fast for passage. In the Kerr case, the ideal math replaces a point singularity with a ring and opens regions where strange paths exist, including closed time-like curves. Those regions live behind horizons in the exact solution and are wrapped in extremes no traveler could survive. Real black holes are born from collapse, pick up matter and magnetic fields, and radiate. Those details change the interior story. The solutions still hint that geometry can be more varied than a simple well with a one-way edge. Singularities mark the limits of our current tools. They are places where curvature grows without bound, and the theory gives no finite answer. To keep such places from affecting the outside, Raj Penrose framed the cosmic censorship idea. Nature hides singularities behind event horizons. If true, no naked singularity can influence distant regions. We can then study gravity's extremes safely, in the sense that signals still obey the rules outside the horizon. Wormhole models complicate the picture. Some contain singular structures in their throats. Some suppose traversable designs avoid them by construction. Whether any real system can sustain a smooth, horizonless, high curvature region without violating other limits is still an open problem. Quantum effects add more texture. Stephen Hawking showed that black holes radiate. Near a horizon, quantum fields allow one partner of a virtual pair to escape while the other falls in, leaving the whole lighter by a tiny amount. Over immense times, a hole shrinks and can evaporate. Small holes go faster. Stellar and supermassive holes take far longer than the current age of the universe. Radiation means black holes have temperatures and entropies. It also raises the information question: how are the details of what fell in encoded in what comes out? Here, ideas that tie entanglement to geometry offer routes to keep bookkeeping consistent, not by letting signals outrun light, but by changing how we count degrees of freedom across the whole system. Speculation about mouths and throats cannot skip the energy book. Ordinary matter has positive energy and focuses light. That focus makes throats close. Exotic support with negative energy density would defocus instead. Quantum theory allows small, brief deficits bounded by inequalities. Whether those bounds can be met in a way that keeps a human-scale throat open is not known. If the bounds are tight, traversable designs fail. If there is slack, careful distributions might work in principle, though engineering would remain far beyond reach. Observations help by narrowing what is allowed. Lensing maps can test for compact, horizonless objects that mimic masses, but lack the shadows black holes cast. Timing of stars near the galactic center puts limits on any extra structure there. Gravitational wave catalogs can be sifted for late-time echoes that a tunnel or horizonless object might produce when perturbed. Transient surveys can search for outbursts that repeat without an engine we know how to model. Every null result lines the path. If no signal appears in a given range, the parameter space for believable wormhole candidates shrinks. The questions return to life and time. If other civilizations step through mouths, their roads would be quiet to us. If no one else exists, the same roads become future tools, if allowed. Closed time-like curves force a rethink of cause. Proposals to keep contradictions away include consistency constraints that allow only loops without conflict, many worlds pictures where changes produce new branches, and protection ideas where feedback prevents loops from forming at useful scales. Each approach comes with tests and with limits. None can be declared final without the full quantum theory of gravity that we still lack. Work toward that theory comes in several forms. String theory ties matter and gravity to tiny vibrating objects and often frames gravity systems as dual to quantum systems without gravity, turning geometry questions into questions about entanglement and computation. Loop approaches quantize areas and volumes, giving a granular spacetime that could remove infinities and replace singular collapse with bounces or finite cores. Holographic tools recast bulk connections as boundary correlations, making phrases like entanglement builds spacetime precise in the models where the duality holds. Each line yields concrete calculations and cross-checks in limited regimes. Large-scale futures set the stakes. As energy thins and stars fade, access to distant reservoirs may become the difference between a culture that stalls and one that adapts. Links, if possible, would move matter and knowledge with little loss. If not, plans would center on long-term storage, slow craft, and the careful use of remaining gradients. Either path benefits from clear physics: what is allowed, what is stable, what breaks under noise. The same clarity helps nearer goals: better clocks, better imaging of compact objects, tighter bounds on energy conditions, and cleaner lab tests of vacuum effects. None of this erases the basic human part. We look up and ask whether the distances on the sky are final or flexible. We build instruments to tell the difference. We try models that stretch what we know and see which parts survive contact with data. Wormholes sit in that process as both a target and a probe. As a target, they challenge us to tie gravity and quantum rules together tightly enough to say yes or no with reasons. As a probe, they force careful accounting of energy, causality, and information, which improves our understanding even if the answer remains not in usable form. The geometry that started with Einstein remains the foundation. Space and time are not a stage, but a participant. Mass and energy shape the stage. Motion and measurement read its clock. Extreme shapes produce black holes. Possible, carefully supported shapes produce wormholes in equations. Between them, live singularities that signal the need for a deeper theory, and horizons that keep dangerous regions from affecting the outside. Quantum rules drape over this structure, adding radiation, limits, and links. Step by step, the combined picture grows sharper. Whether it contains large, traversable tunnels or only tiny, non-traversable links, the work needed to tell the difference keeps revealing how the universe holds together at its smallest and largest scales. Hawking's result that black holes radiate raises a direct question for any tunnel tied to a hole. If a mouth is anchored to a black hole that slowly evaporates, does the evaporation also drain the support for the tunnel? If the hole shrinks, Does the throat narrow and collapse, or can the tunnel remain as a freestanding link between two regions after the anchor fades? Our present tools do not give a firm answer. The calculation needs the full machinery of quantum gravity, a theory that treats curved spacetime and quantum fields at once and follows their back-and-forth influence over long times. Open puzzles like this sit next to larger unknowns about the contents of the cosmos. Observations show that most of the universe is not made of the atoms we know. Dark matter behaves like invisible mass. It pulls on stars and gas, binds galaxies, and sculpts webs on the largest scales. We infer its presence from motion and lensing, yet no detector on Earth has directly caught a dark matter particle. Dark energy acts differently. It drives the expansion to speed up, as if space has a built-in push. In simple models, it sits in the equations as a smooth energy with negative pressure. That negative pressure is not the same thing as negative energy density, but it does make gravity act repulsively on cosmic scales. Speculation connects these ingredients to exotic support. If something with negative pressure can stretch the fabric of space, could a related effect help hold a throat open? The idea is tempting, but unproven. Dark energy, as measured so far, is diffuse and gentle, spread thin across the universe. A traversable throat would need concentrated, local, negative energy density. Dark matter might also invite ideas. If it turns out to be a new field or a mix of particles with unusual interactions, creative models could try to use it to shape geometry. None of this rests on evidence today. It is useful mainly as a reminder that the inventory of matter and energy is not complete, which leaves room for new physics that may change how we think about strong curvature. The information paradox returns here because it ties quantum rules to curved geometry. In classical relativity, whatever crosses a horizon is gone to the outside world. In quantum theory, information cannot be destroyed. It can be scrambled beyond easy recovery, but the total bookkeeping must balance. Hawking radiation makes holes shrink, so the question becomes sharper. How is the information about what fell in encoded in what comes out? Over the last decade, work that combines gravity and quantum information has made progress. Calculations that track the entropy of Hawking radiation suggest that, in consistent models, the radiation's information content rises and then falls in a page curve, matching the expectation that total information is preserved. In many of these setups, entanglement plays the central role, and the geometric language that goes with it looks wormhole-like. The ER equals EPR idea puts this in a slogan. Strong entanglement between two systems can be represented, in the gravity picture, by a non-traversable wormhole connecting them. Nothing travels through that connection, but the correlation structure can keep the books straight. Extensions of the basic picture ask whether extra spatial dimensions change the balance. String theory places matter and forces on tiny vibrating strings in a space with more than 4 dimensions, often 10 or 11. Most extra directions are curled up too small to see. In such settings, links between regions can take new forms. Brain world models. Imagine our visible universe as a 3-dimensional brain floating in a higher dimensional bulk. Another brain could sit nearby in an extra direction. A wormhole in the bulk might connect points on different brains. The demands on energy conditions can shift in these frameworks, sometimes lowering the amount of exotic support needed in the 4-dimensional slice we inhabit. These are model-building exercises, not observations, but they show how sensitive throat physics is to the arena in which it plays out. Closely related is the holographic principle. From black hole thermodynamics came the insight that the information capacity of a region with gravity scales with its boundary area rather than its volume. In controlled examples, certain gravitational systems are exactly dual to quantum systems without gravity that live on a lower dimensional boundary. In those dualities, the connectivity of the bulk, whether two regions are linked by a non-traversable wormhole, maps to patterns of entanglement on the boundary. Break entanglement, and the bulk can tear. Increase it, and the bulk can fuse. In that language, a wormhole is not a literal tunnel carved into a pre-existing stage, but an emergent feature built from correlations. The prospect of describing geometry as organized information ties several threads together. Black hole, evaporation, ER equals EPR, and the kinds of support a throat would need. Ideas about the early universe add another venue. In the first fractions of a second, the densities and temperatures were extreme, and quantum fluctuations were strong. On the tiniest scales, space-time may have behaved like foam, with short-lived bridges and bubbles appearing and disappearing. If a brief phase of rapid expansion cosmic inflation occurred, anything present before it began would have been stretched to large sizes. A microscopic tunnel, seeded in that foam, could, in principle, be pulled to macroscopic scale. Most such structures would not survive interactions with later matter and radiation, but a rare survivor might. Searching for a primordial wormhole would rely on the same tools already used to map dark, compact objects, lensing patterns that do not fit black hole models, odd signatures in gravitational waves, or precise timing anomalies where a horizonless mass would behave differently from a standard hole. These physical possibilities come with responsibilities. If a civilization could build or use a traversable throat, the power to move people and resources instantly across great distances would force new rules. Placement near inhabited systems would need safety margins so that lensing does not disrupt orbits or concentrate radiation. Traffic would need to be metered to avoid stress on the support fields. If time offsets can be created by motion or gravity, policies would have to address contact between regions with different local histories. A simple principle like "do no harm" becomes richer when a path through space might also be a path through time. Oversight would need technical and ethical arms, audits of the geometry, and debates about acceptable use. Even before engineering arrives, the questions touch meaning. If short paths exist, where long ones seem to rule, distance is not only miles on a map, it is a feature of the stage those miles sit on. If an offset can loop a world line back to an earlier event without contradiction, then cause must be defined carefully, not just by calendar order. These are not invitations to abandon clarity. They are prompts to be precise about words like before, after, same, and elsewhere, when geometry itself can be shaped. Open problems continue to set the agenda. Does a mouth tied to an evaporating hole fade with it? Or can a free throat persist under semi-classical back reaction? How tight are quantum inequalities in dynamic spacetimes, where the geometry changes quickly instead of sitting still? Can negative energy be arranged in thin layers or pulses that meet the bounds and still keep a throat open long enough for passage? In modified gravity theories that pass known tests, do the effective energy conditions relax in ways that materially change stability, or do new instabilities appear? Are there clear, multi-messenger signatures that separate a horizonless compact object from a black hole across lensing, dynamics, spectra, and waves? Work on these fronts is concrete, Observatories that image black hole shadows tighten models of strong fields. Pulsar timing arrays add sensitivity to tiny accelerations that would betray unusual nearby masses. Gravitational wave catalogs grow, and analysts search for late-time echoes or mode patterns that differ from Kerr black hole predictions. Laboratory experiments refine measurements of vacuum forces, testing the bounds on negative energy and for how long it can be maintained in controlled setups. Quantum simulators engineered systems whose equations match those of harder targets let researchers study information flow and entanglement growth in cases that mirror simplified gravity duals. Higher dimensional models and holographic dualities provide testbeds where hard questions can be asked in well-defined ways. In some dual pairs, a statement about a wormhole's existence maps to a statement about a correlation pattern that can be computed. In others, a page curve-like recovery of information can be traced step by step. None of this replaces observation, but it disciplines speculation and points to signals that matter in the sky. Singularities and censorship remain important in the same context. A traversable design aims to avoid singular cause and event horizons by construction, replacing them with smooth, high-curvature regions supported by tailored stress energy. Proving that such regions can exist without hidden failures is part of the task. If cosmic censorship holds strictly, then attempts to expose singular behavior might fail in all realistic settings, replaced by horizons or by quantum effects that smooth the core. If censorship can be violated under certain conditions, observation would have to be ready to tell a naked singularity apart from any horizonless mimic, a job for lensing maps, dynamical tests, and spectra. Hawking radiation closes the loop with lifespan. Large holes are cold and fade slowly. Small holes are hot and fade more quickly. If a mouth is linked to a shrinking hole, it lives in a changing environment where the support conditions drift. The back reaction of quantum fields can either nudge a system towards stability or away from it, depending on the configuration. Following that evolution in detail would tell us whether tunnels can persist in an evaporating landscape or whether the geometry closes as the anchor weakens. Speculation about dark components adds further paths to check. If dark energy is truly a cosmological constant, uniform in time and space, it helps set the large-scale shape of the universe, but offers no local handle to tune. If it evolves, or if it emerges from fields with structure, its small-scale behavior could matter. If dark matter is a single particle type, mostly cold and slow, it behaves like a pressureless fluid that clusters. If it is warm, self-interacting, or part of a richer sector, its gravitational influence and its coupling to other fields could differ in ways that affect compact structures. Each scenario has observational consequences independent of wormholes, and those consequences can be used to bound what is possible for any throat that would rely on such ingredients. Across all of this, the steady approach stays the same. Define clean targets, derive signals that differ from ordinary compact objects, build instruments that can see those differences, test energy bounds in the lab and in theory, use dualities and models to sharpen claims about how information and geometry connect. Treat ethical and governance questions as part of the design space, not an afterthought. Keep language plain and claims modest, since the topic is strong enough without decoration. The questions do not exhaust themselves, and the lack of a final theory does not prevent progress. Each new limit on negative energy, each sharper image of a compact object, each cleaner gravitational wave event that matches or defies standard templates narrows the options. Step by step, the path forks toward two outcomes that both teach us something clear. If traversable throats at useful scales are ruled out by firm quantum bounds or by unavoidable instabilities, then causality's protections are stronger than the early equations suggested, and distance keeps its old meaning in practice. If a set of signals converges on a consistent, horizonless object that lenses, vibrates, and moves like a supported throat, then geometry has more room to maneuver than we thought, and the tools of travel can, at least in principle, include links that redraw the map. Between those edges lies the daily work: telescopes watching for odd lenses, detectors listening for unusual echoes, clocks marking tiny tugs, and calculations that tie correlation to connection. Each result, even a quiet one, refines what wormholes must be like if they are part of nature, and what they cannot be if they are not.